Hello everyone and welcome to Selected Homework Problems. We're going to start with number 56. We're going to start with number 156 because 56 isn't on here. Use a fundamental theorem of calculus to find this derivative, 156. So here we are. We are looking at the derivative with respect to x of the integral from 1 to the square root of x of t squared divided by 1 plus t to the fourth dt. So remember, for these fundamental theorem of calculus part 1 problems, is that it really doesn't matter what's on the inside. Essentially what's happening is we just replace all the t's with whatever's up here, and we use the chain rule to multiply by the derivative of whatever's up there. All right, the actual one has a little bit more subtleties, right? This has to be a constant. Integrand has to be continuous. And this one does have that. We got a constant, we got a continuous integrand. Remember just the inside, the function inside the integral. So we can just do the thing and simplify. So t squared becomes the square root of x squared. T to the fourth becomes the square root of x to the fourth. And if it were just x's, that would be it. Just the integrand evaluated up here. But because it's not just an x, it's a function of x, we have to use the chain rule. Anytime we take the derivative of something where this variable is messier, to multiply by the derivative of the inside. And in the fundamental theorem of calculus video part 1 examples, I show why that's the case. 1.3.3 is where that's mentioned if you want some more on that. We have to multiply by the derivative of the square root of x. And remember, square root of x is the same as x to the 1/2. So you have to be a little bit careful here because I don't believe this function gives us our domain. No, so we don't know what x is. X could be positive, x could be negative. X doesn't have to be bigger than 1. Remember that this integral over here makes sense even if x is less than 1. So the square root of x squared doesn't perfectly cancel each other out unless x is positive. So we're going to say this is actually the absolute value of x. No, it's not. The opposite is true. If we switch the squared and the square root, it is just x. But this only makes sense for x being positive because we're not taking the square root of negative number. We're not worrying about imaginary numbers here. So we are going to write it as an x and this as an x squared, but we will be specifying that x has to be non-negative. Derivative of x to the 1/2 is, we'll use the power rule to get x divided by, this becomes the square root of x in the denominator, square root of x times 1 plus x squared. And now I actually don't have to write this anymore. This becomes redundant because implicit in this formulation, we know that x has to be strictly positive. If x is 0, this doesn't make sense. We're dividing by 0. And if x is negative, we're going to, again, have imaginary numbers. So we're only dealing with real numbers, so actually this is sufficient here. This is our derivative. And again, I shouldn't have skipped this step. What's really happening here, we're multiplying by 1 divided by 2 square root of x, because these things are the same. Negative exponent moves it to the denominator, but it's only attached to the x. And then, that's why you don't skip steps, folks. And then the 2 and the square root of x come out in front. We usually like the top distributed out and the bottom fully factored. So there we go. That should be the final answer. Here we are. Let me know if you ever notice any mistakes on these videos, please. You will get an extra credit point for that. Okay, next problem, 160. The graph of this integral function, where f is piecewise constant shown below. No. Hold on. The graph of y is shown below. This is the graph of y. This is not the graph of f. This is the graph of that area function. Over what intervals is the integrand positive? Oof. All right, so let's make this easier. Let's use the fundamental theorem of calculus to make this problem much, much easier. Okay? Because in number 160, we know that y is the integral from 0 to x of f of t dt, and y is what's graphed. So I'm going to use the fundamental theorem of calculus to find y prime. Fundamental theorem of calculus is not able to be used here. Ha! Okay, this problem is a little messier than I thought it was going to be. I can't use the fundamental theorem of calculus. Why? Because the fundamental theorem of calculus requires, this is a good learning opportunity, requires that this integrand, which does need a dt, requires that this integrand is continuous. But we know that it's not necessarily continuous. We're told that f is, the integrand is a piecewise constant function. Most piecewise functions are not continuous. They can be. All right, so there's a couple ways of going through this. We could actually graph f exactly, but it's kind of tricky. Oh man, all right, this problem is, all right, is harder than I thought. So it's a good thing I'm doing this video for you guys. I'm going to copy this information down. I'm going to copy this graph down. It's going to be much more straightforward when I'm not tabbing back and forth here. Okay. Specifically, I need to actually remember to use the graph paper. And we're going up to 4 and up to 6. All right. So 1, 2, 3, 4, 5 is here. 6 is here. And then 1, 2, 3, 4. 4 is right here. We're starting at 0, 0. And then we're going to 1, 3. That was supposed to be a straight line using the straight line tool. 0, 0 to 1, 3. 1, 3 to 2, 2. 2, 2 to 3, 0. 3, 0 to 4, 3. Constant, and then it goes down 1. All right. So this is going to be a little easier to do. So this red graph is a red graph of y, and it shows the area under f. So for me personally, what I think is the easiest is to actually draw f. We know f is piecewise constant, which means it's constant on every single piece. So you can see what the pieces are going to look like. There's going to be one piece that looks like from 0 to 1, another piece from 1 to 2, another piece, and so on. And we'll probably be able to figure out a pattern. Because specifically, we know exactly what the function is from 0 to 1 because y, which is when x is equal to 1, we know y is equal to 3 because this point is on the graph. So that tells us that the integral from 0 to 1 of this function is equal to 3. Why is that useful? Because we know this is constant on that piece. So what the integral, the area under a constant function, is going to be a rectangle. The width is 1. The height is 3. So we know that this function f starts like that. We don't know where the open circle is. We don't know where the closed circle is. It won't, I think, hopefully matter for this problem. We'll just guess that it's a closed circle here. It doesn't actually probably turn out to matter. And we're going to do the same thing. So next up, let's look at the next piece. The next piece is when x is equal to 2, y is equal to 3. Sorry, when x is equal to 2, y is equal to 2. So that tells us the integral from 0 to 2 of this function is equal to 2. There might be a nicer way of doing this. This is the way that jumps to mind. So if the area is 3, but now the integral becomes 2, we've lost 1. How do we lose 1 in the interval from 1 to 2? Right? This tells us by our properties of definite integrals that the integral from 1 to 2 of this function is -1. So the piecewise function actually jumps down to -1 here. Because this plus this needs to equal that. Integral from 0 to 1 plus 1 to 2 needs to equal 0 to 2. All right, and so on. You can use this procedure to continue. We need negative numbers. I didn't know we did, but we do. Follow the same line of logic. This next one goes down by 2 again, or by 2 instead of just down by 1. You can follow the same logic to get this. And then it's going to go back up to 3. Then it's going to be at 0. And it's going to go down to -1. So this is our function f. I don't think it necessarily wanted you to graph f, but I think it's a useful practice for definite integrals to graph this function f. You don't have to, though. And I'll try to show, if I can explain so in a clear way, I would try to show both ways of doing number 160. All right, so let's start with part A. And I'm going to lose the graph paper. Part A say, over which intervals is f positive? And which is it negative? And which is it 0? So of course, since we already graphed the function, we can do this immediately. But let's forget about the blue graph. Remember that f is the function that we're integrating over. F is the function that we're looking at the positive or negative area. So if f is positive, then as x increases, the area goes up. If f is positive, y is increasing. If f is negative, y is decreasing. So f being positive is just the same thing as the function being increasing. Think of the connection between, oh, it's not showing up my cursor. You're not seeing what I'm gesturing to. And it won't show the cursor unless I click. But if I click on the window, something weird usually happens. But if I click on the scroll bar, maybe I'll be okay. So if f is increasing, so if y is increasing, if y is a positive slope, then f has to be positive. Because we're adding area. Okay, and that's what's going on here. So that's the connection. And you can see that with our graph over here as well, right? If the slope of the red is positive, that means blue is positive. All right. And essentially blue is just the slope. And if this were continuous, if this function were continuous, blue would literally be the slope. But because it's a piecewise constant function, the derivative doesn't exist at these points. All right. So really, might be best. We don't know what f is. F could be a couple different things here. F actually could be infinitely many things. They could both be open circles and f could be up here and it wouldn't change anything. So we don't know what f is. This is one f. There could be multiple f's. And we don't know. And that's a discussion for another time, why we don't know. And that's a long explanation. The idea is f is positive when the function's increasing, which is 0 to 1, and 3 to 4. And f is negative when the function's decreasing, which is from 1 to 3 and 5 to 6. And we're using open intervals here on purpose. Finally, f is constant. Go back to Calc 1, increasing and decreasing for usually why we do open circles for that. And then again, it's reinforced by the fact that there's infinitely many f's that have this be the case, which again really goes into some very fascinating aspects of mathematics that get pretty complicated. That's what we have for part A. Part B, what are the maximum and minimum values of f? Well, if we can think of f as roughly the slope, again, it's not really the slope because the slope doesn't exist at all points. If you think of f as roughly the slope, it's going to be the biggest, well, when the slope of y is the biggest. Because if this were continuous, we could use the fundamental theorem of calculus and it'd be much easier. But it's not. So we can't. All right, so from 0 to 1 and 3 to 4. And you can see that over here. Yes, it's biggest from 0 to 1 and 3 to 4. F is biggest on 0 to 1 and from 3 to 4. Finally, part C, what's the average value of f? Again, we could calculate it using our formula for the average value of a function, or we could try to do it in a clever way, which I have to think of. The average value of f. Because remember, this is not the function. This is the integral of the function. And it's not jumping to mind, because there's a couple of things that we might think of. We might think of, oh, at 6, we got integral from 0 to 6 of the function, but that gives you the average value of y, which is not what we want. Yeah, I'm sure there's a clever way, but I don't want to slow down the video, so I'm just going to go and do the regular way. We can find the average value the straightforward way. We'll call it that one, by just looking at the integral of blue, which is positive 3 minus 1 minus 2. So that's 0. Plus 3 plus another 3. Oh. Sorry. Plus 3 plus 0 minus 1, so it should be 2. The area, the integral of the blue one from 0 to 6 should be 2. The average value should be 2 divided by the integral f from 0 to 6. Oh, there we go. I was right. There is a smart way of doing it. All right, the average value of, goodness, I am out of it today. The average value of f is just 1 over b minus a, the integral from 0 to 6 of f of t dt. But we know this is just the y value when x equals 6. When x equals 6, the y value is 2. This is consistent with what we said earlier. So this is just 1/6 times 2, or 1/3. And you can see, again, that 1/3, if you did kind of plot it. The idea is that the blue graph, the area below this line to the blue graph and the area above this line to the blue graph should be about the same, which looks plausible. Goodness. All right, next problem. 166. Use a calculator to estimate the area under the curve by computing T10, which is the average of the left and right endpoint Riemann sums. So we're going to use that website to do it, so you don't have to do it by hand. And then, so that's going to be our first step. And then we'll use FTC to determine the actual area. So for 166, that's y equals the square root of x cubed. And we're looking at the interval from 0 to 6. So L10 for this, we can use that calculator. Square root of x cubed from 0 to, what was it, 6? 10 subintervals. The left endpoint, by the way, the average of the left Riemann sum and the right Riemann sum, I do not believe in general is equal to the midpoint Riemann sum. I could prove that one way or the other, but that's a conversation for another time. Oh, this is going to spoil the answer. But what we have, wait, this is a pen. This is not my actual tablet pen. It is late in the day. All right, so the Riemann sum will be 30.9667. Or you could write the exact. Oh no, the exact is just the integral. 30.9667. And the right is going to be 39.7849. So quite different, 30 and 40 basically. And if we calculate the average right there, the average of 30.9667 and 39.7849, that's going to be 35.3758. That's what the book is calling T sub 10. Just to make sure that I'm not crazy, this won't prove it one way or the other, but it might disprove it. The midpoint, 35.22. All right, great. So midpoint is not the same as the average of the left and right endpoints, which is what I thought, but I wanted to confirm. All right, so it wanted us to find this T sub 10, and then it wanted us to compare this to the actual. So we know the actual area is an integral from 0 to 6 of x to the 3 halves dx. Remember, we can rewrite this with rational exponents to make it easier to use the power rule. So we're going to add an exponent, divide by that exponent, and evaluate it from 0 to 6. We can factor out a 2/5 if we'd like, and then plug in 6 to the 5 halves, and then plug in 0. And we're just going to get 6 to the 5 halves. A couple of ways of simplifying that. And if the only reason we have this is to compare with the other one. So a lot of times I want exact answers, and we can simplify this a little bit. But if we're just trying to compare, let's just plug this in. 2/5 times 6 raised to the 5 halves. 35.2727. So let's compare these. And they look pretty similar, pretty close. In general, they may or may not be close, and there's a lot of theory about when they're going to be close and when they're not going to be close. But they'll be a heck of a lot closer than these, I'll tell you that much. In general. Okay, so that's pretty much what we got. We can even double check that, hey, this is the same thing, and I said there's ways of simplifying it. If we did, that's what it'd look like. So that's that problem. Next up is 180. Roll down a bit. All right, just evaluate. The integral from 1 to 4 of 2 minus root t. Nah, this is way too similar to the one we did in the lecture. Let's do 182. The integral from 0 to 2 pi cosine of theta d theta. All right, this gives us extra practice with a different variable. I need to make a note already that I'm switching 180, 182, so I don't mislabel anything in your video. And note has been made. So we need the antiderivative of cosine. Remember, that's the derivative of what is going to equal cosine. Our answer is going to be negative sine. You can also find that in your table. In not this table, where did the other tabs go? I think I separated them. Yep, I accidentally separated them. In this table, antiderivative of cosine is indeed, wait, what? Positive sine, because the derivative of positive sine is positive cosine. Woohoo! Okay. Let's put my window back where it belongs. All right, so our answer is sine. Sine is the antiderivative of cosine. So this is going to be sine of theta, evaluated at 0 and 2 pi, and we're taking the difference. So we get sine of 2 pi, which is 0, minus the sine of 0, which is 0. And this definite integral should make sense, because graphically, what's going on, let's connect some concepts, is we're looking at the cosine of theta. I'm just going to write as y equals cosine of x here for Desmos. We're looking at this between 0 and 2 pi. And we're looking at the signed, the net signed area under the curve. And I'm saying it's 0 because the area below the curve is the same as the area above the curve. And this is a periodic function, so it's a lot easier to see. It's exactly the same as looking at this integral. This is indeed the same area as that. And for net signed area, we count this as negative. Same for integrals. Integrals use net signed area. So it should not be super surprising if you know the graph that this answer is 0. 196. Oh, in the video, I wanted to do 180 and 182. In my original notes, I accidentally moved this thing again. Oh no, this is one of those days, my friend. These other ones, you just write them as rational exponents. We did a trig one. Yeah, all of them are just writing as natural exponent. Oh, no, okay, this is a little different. Let's do 172. So 180 went to 182, and then 182 went to 172. I just want to make sure to give you guys some different examples. The integral from -2 to 3 of t plus 2 times t minus 3. We do not currently have a product rule for antiderivatives. The derivative of what equals this? That's going to be messy. Eventually, we'll talk about integration by parts, which functions similarly. But even once we have integration by parts, we're not going to use it on this problem. We're going to FOIL. Okay, let's simplify this. FOIL this out. We're going to get t squared plus 2t minus 3t is minus 1t. And then minus 6 is our last one. And now we can use the power rule on this. We'll get t cubed times a third minus t squared times a half minus 6t, all evaluated between -2 and 3. And again, if you want, you can write this as f of 3 minus f of -2, and you can calculate these on the other side. This red method, I think, is maybe a little easier, a little less messy. The white method is just, the method that I'm writing in white is a little bit more common, I think, but feel free to calculate it out in the red. So we plug in 3, watch out for making errors. we're going to get 9 minus 9 halves minus 18 minus, when we plug in -2, we'll get -8/3 minus 2 plus 12, and we can keep simplifying. 9 minus 18 is -9. -9 minus 9 halves is -27 halves. Minus, we get 10 minus 8/3. That's 22/3. And this one's not doing in my head. -81/6 minus 44/6 is -125/6, which shouldn't simplify. This one, I'm definitely checking my answer. I should have used the calculator. I should not have tried to do that by hand. The integral from -2 to 3 of t plus 2, t minus 3 dt is that. Is that what we had? I think it is. -125/6. Great. So just be very careful with the algebra. Use a calculator, check your answer. Maybe try to do it by hand and try to use a calculator. And then make sure the answers are the same on these ones. Now we'll do 196. Yeah, I specifically chose this one because I thought it'd be kind of tricky. For many students probably won't have seen something like this before. Identify the roots of the integrand to remove absolute values. Before we even start this problem, I want to explain what that means. So let's look at the relationship between x and absolute value of x. And we're going to do this graphically. I really want to explain what's happening here, why they phrase it the way they do. So absolute value of x is just the same graph as x, except the only difference is where x would go negative, instead of going negative, absolute value turns it positive. It bounces it off the axis. Similarly, if we look at the absolute value of sine of x, that should look very similar to sine of x. The only difference is where the blue graph would go negative, instead of going down, it bounces off and becomes positive. So when it says find the roots, remember the roots of the integrand is the inside. So the roots are just where the function equals 0. Because if these are continuous functions, and all of these are continuous functions, remember the intermediate value theorem says that the only way a continuous function can go from positive to negative or vice versa is when it's 0. Okay? So that's why we're finding when the function is 0. And that's important because that helps us find the integral of an absolute value. We don't have any fancy formulas for integrals of absolute values. Look them up. They don't exist. If they do, tell me. I'd love to hear about them. And that's not sarcasm. 99% sure they don't exist, and I know they don't exist in this class. So what we're going to use is this method to evaluate them. Because you can't just, like if I want to know the area under this green curve, the only way to do it is to look at this blue curve, which we can find integrals of, and then say, okay, let's add this integral. And then from this interval, we're going to get a negative answer. Let's turn that negative answer positive, and we'll add this positive with this positive. We have to kind of force it to be positive. So that's really what's going on in this problem. We're looking at the integral. All right, graphically, we already kind of did it. The integral from 0 to pi of cosine of t dt. Now, if you're really good at graphing trig functions, this problem becomes way easier. In fact, that's true for all these functions in this chunk. If you can graph it, graphing it is much easier. But this is a question that you could see on a quiz where you don't have access to Desmos. And if you can grab it by hand, that's great. That's going to make your life easier graphing it by hand. But you don't need to. Let's see where is cosine positive and where is it negative. Sorry, we needed absolute values. To answer this, if we know where cosine's positive and where it's negative, we can do this. We can get rid of the absolute values. Watch how. We'll start by saying where is cosine of t equal to 0 on the interval. That's what it says. That's what it means when it says find the roots first. So we're going to look for this, and well, we can solve this by using a unit circle. Cosine is the x-coordinate on a unit circle. So it's at these angles. What are these angles? These angles are pi over 2, negative pi over 2, 3 pi over 2, etc. It goes in both directions. But only pi over 2 is in that interval. This is the only place it changes from positive to negative. So we can set up one of these little charts like we've done before for remember using the first derivative test and stuff like that. If cosine's continuous and the only place it can change from positive to negative is right here, then everything in this interval has to have the same sign and everything in this interval has to have the same sign. So if we want to know where cosine's positive and where it's negative, all we have to do is just plug something in here, plug something in here, and see if it's positive or negative. So if we look at cosine of pi over, well, I guess cosine, we don't even need to do this, right? We know cosine's positive in the first two quadrants. No, we don't. We know cosine's positive in the first quadrant. Sine's positive in the second quadrant. So we know cosine's positive here, negative here. Or, if you didn't remember that, you could plug in some numbers in these intervals to find that as well. So why does this matter? Because we can't really integrate absolute values. So we need to rewrite this without absolute values. How do we do that? How do you rewrite the absolute value of -2 without absolute values? You just make it positive. Let me make it positive in this way. How do you rewrite -x with an absolute value? It's the same thing. You just add a negative. Negative doesn't necessarily mean negative. Negative means opposite. The opposite of opposite gets you back where you started. So if cosine's negative on an interval, we can make it positive by just adding a negative in front. And then it'll be positive. So this integral is exactly the integral from 0 to pi over 2 on this interval. Absolute value is redundant. From 0 to pi over 2, cosine's positive anyway, or 0. So that's equal to the cosine of t dt in that integral. And then we're looking at the integral from pi over 2 to pi, and we know cosine's negative, and we want to turn it positive. We're going to write it as negative cosine of t dt. And now this is a positive function, and now this is a positive function. And before we continue, if you doubt me, first on, doubt is healthy, I can show you. Cosine of t, where t is between 0 and pi over 2, looks like that. And then negative cosine of t, where t is between pi over 2, oops, that's not how you write that. T is between pi over 2 and pi. See how we're forcing it to bounce off, because normally without the negative, it'd continue going on down there. So we're just forcing it to bounce off by adding another negative, and the negatives cancel and we get positive. So that's another way of seeing what's going on here. And then we can just calculate these as before. The derivative of the derivative of sine is cosine. So the antiderivative of cosine is sine. So we'll get the sine of t between 0 and pi over 2 minus, right, there's that minus sign here. We can bring that out in front. Minus the, again, same antiderivative, cosine of t from pi over 2 to pi. and proceed down this way. That'll give us the sine of pi over 2 minus the sine of 0 minus, let's make sure to use parentheses, cosine of pi minus cosine of pi over 2. So that's going to equal 1. The sine is the y coordinate on the unit circle, minus 0. There's a y coordinate 0 at an angle of 0, minus cosine of pi. Cosine's the x coordinate, it's negative 1. Minus cosine of pi over 2, again, the x coordinate there is 0. And we get the total area is just 2. Interesting. Has nothing to do with pi at all. The area. Really nice how that works out. Nice number area. Let's do the last problem here. Where am I? I need my brain to start working. I really need my brain to start working before we read this guy. Suppose the number of hours in daylight in a given day in Seattle, hey, is modeled by the function. I'm going to write that down. I'm going to call it f of t. We're not really should have written f of t here. Negative 3.75 cosine of pi over 6t plus 12.25. Where t is given in months and t equals 0 is the winter solstice, which is like December. Oh, I'm going to embarrass myself. It's somewhere around December 21st. It probably tells me. Maybe. All right. T equals 0, winter solstice. All right. You know what? Let's just Google it. Hey, December 21st. Great. Woo. Wasn't even worried. Use American date form. It's 12/21. Otherwise, 12/21 doesn't really mean anything. Let's move on. I can do something that doesn't require my brain. Like eat. That would be a good idea, actually. Oh yeah, I forgot to eat lunch today. Don't do math on an empty stomach. They're a bonus lesson for all you guys. 198. It is 4:45, so not a great time to have realized you forgot lunch. What's the average number of daylight hours in a year? Well, the number of hours of daylight is this function. So the average amount of daylight in an entire year is going to be with the average value function. A year is 12 months. You're welcome. We got the integral. Honestly, I'm surprised I knew a year is 12 months with how my brain's working right now. The integral from 0 to 12 of this function. And we just calculate this all out. So let's do it. That's our average value, our average number of daylight. We get 1/12 times the integral from 0 to 12 of this function. This is negative 3.75. Cosine of pi over t. We're going to have another like chain rule type thing going on here. Plus 12.25 with respect to t. Find the antiderivative here. Antiderivative of cosine is sine. But we have to multiply by 6 over pi. Because we have a pi over 6 on the inside. All right, and again, you can check that this works by taking the derivative of this and seeing that it is indeed the thing above because of the chain rule. And we'll formalize this process in, I believe, 1.5 when we talk about substitution methods. It's 12.25t is our antiderivative evaluated from 0 to 12. So call this f, this function f of t. And what we're going to do is we're going to say what's 1/12 times f of 12 minus f of 0. And I'm going to use a calculator. So here's what I'm going to do. I'm going to write negative 3.75 times 6 over pi sine of pi over 6 times 12 plus 12.25. We should know the answer, by the way. Just what we know about the world and how the world works. I have an expectation for the answer. This should be f of 12. Okay. Now we subtract f of 0. And f of 0, let's just copy it down and replace the 12s with zeros. Wait. Sorry. I'm getting confused with how Desmos is treating these parentheses. Why does it say that it needs an extra parenthesis? On parenthesis, off parenthesis, on and then off. It's just being weird. There we go. Now it's being normal. And now we plug in 0. There are only two places where we plug in the things. F of 0 is 0, so f of 12 is 147, f of 0 is 0. So we're going to get 147 divided by 12, and we're going to get 12.25. We should have expected the answer to be about 12. Now, this isn't a perfect model, but yes, on average, there's 12 hours of daylight. You live on the equator, 12 hours of daylight. Live off the equator, it'll average out. And this isn't a perfect model, but that's how we use it. There it is. That's part A. Let's do part B. And then part C, and then lunchtime. 5 o'clock lunchtime. Right at what? Oh, there's also part C. At what times, T1 and T2, in order, do the number of daylight hours equal the average number? Okay. So we should have a guess if we just know how the world works. Should have a guess. I have a guess. I'm not going to spoil it for you. Let's do it mathematically. Okay. And we know this is a continuous function. It's partially cosine and partially a constant function, continuous. So because we're taking the integral of a continuous function, we know that there has to be a point where this integrand, the average of that integrand equals a function value at some c. There's at least one c, and the book is telling you actually that there's two here. We could try to calculate that by solving. So let's do it instead of doing it by hand. So we're curious, when is the average value equal to the function? Well, we know the average, we found the average value is 12.25. When is that equal to the function? Well, the function's 3.75 cosine of pi over 6 times t plus 12.25. There's another way, by the way, of knowing that the average is going to be 12.25 for this problem, right? I didn't even think about it, but this is cosine. Cosine normally has a period of 2 pi. But if you horizontally compress it by a factor of pi over 6, which is what we're doing, then it now has a period of 12. And the average value of cosine over one period is just going to be 0. So the average value of this whole thing is 12.25. Okay. All right. So let's get some trig practice. Let's subtract 12.25 from both sides. And we're going to get, okay, when is t equal to 0 like this? Or when is this thing equal to 0? Solve for t. We can divide both sides by this guy. It doesn't do anything. This is the amplitude. Amplitude doesn't have to do with averages. Not really. Well, if the midline is 0. Anyway, if we're going on a period, amplitude doesn't really matter. And we get when is cosine. And again, remember our interval. T is only between 0 and 12. We need to solve this. We're going to do a substitution. Remember your trigonometry. let u be pi over 6t. So if t is from 0 to 12, what's u? Well, when t is 0, this is a linear substitution, so this works this way. We can just plug in both sides. When t is 0, u is 0. When t is 12, u is 2 pi. So we're really just solving this equation. When is cosine of u equal to 0? Again, we're going to go back to our unit circle. Cosine's the x-coordinate. When is the x-coordinate equal to 0? Twice. Pi over 2 and 3 pi over 2. Those are the two coordinates that are in this interval. If it were 0 to 4 pi, we'd have two more answers. 0 to 6 pi, two more answers. Negative 2 pi to 2 pi, two more answers. All right. So these are our answers. That's what u is. That's not that helpful, though. We want to know what t is. U is pi over 6t, so just replace it. So when pi over 6t equals pi over 2, and when pi over 6t equals 3 pi over 2. Multiply both sides by 6 over pi, and you're going to get t is equal to 3 and 9. So that's the equinox, right? Winter solstice, 6 months later, summer solstice. 3 months in between is I think it's called the equinox, right? I should know these things. But what's the phrasing of the problem? At what times? Okay, here are the times. T1 equals 3, and the second time equals 9. So March 21st and September 21st. And now we do part C and then part D and then dinner time, lunchtime, sorry. Write an integral that expresses the total number of daylight hours, between these two equinoxes, like spring equinox and fall equinox. Is that what they're called, I think? The total number of daylight hours between that is just going to be the integral. Adding them all up. Adding up all the days. Now, in actuality, because the number of days between these two things is a discrete valued function, the integral is actually not giving you an exact answer. You could actually add up. Day 1 has this, day 2 has this, day 3 is this. That's what you'd have to do to get the exact answer. So in this case, we're approximating a Riemann sum with an integral, but you know, let's not split hairs today. Integral from 3 to 9 of this function dt. And we just have to write it. We wrote it. That's done. And then part D, what is the average number of daylight between T1 and T2? And then between T2 and T1. And then show that the average of the two, so from March to September and then September to the next March, not asking for you to go backwards necessarily, but it will be equivalent. And show that the average of the two is equal to the average day length. Okay, let's get to it. This is the thing, though. It has different parts, but part D, that's really 3 more parts. They trick you just the same way I trick you guys. Oh gosh. All right, the average number of daylight between T1 and T2 is going to be 1 over 6. An integral from 3 to 9 because there's 6 months between March and September of this function. Now we already figured this out, right? It's just 1/6 times f of 9 minus f of 3. We already had that set up, so let's just use that calculator again. This is 9 up here. And this is 3 down here. So that number minus that number divided by 6. Going to be 14.6373. that many hours. So between spring and fall, if we're in the northern hemisphere, which we're in Seattle, so we are, between spring and fall, the average daylight is 14 and a half hours. For anyone who's lived in this area for a while, you know that, well, if we do the next part, which says find the integral, the average from September to March, we got shorter days than that. This is like the part 2 of part D. All right, which is again going to be 1/6 times, this is going to be capital F of 3 minus capital F of 9. All we have to do in these calculations over here is switch the order of the subtraction. We'll turn that one positive and that one negative. I need to eat some food. Okay, so let me reread the problem. Compute the average number hours of daylight between T1, which is 3, and T2, which is 9. So, all right, so B minus A over here is -6 for starters. I don't see how this is not just also 14. The negative is taken care of, right? Because B minus A is different. It shouldn't be 14 anymore. What am I missing? I'm missing something. I'll make a little note because this is the last part of the problem. I'll make a little note about what I'm missing. I need it. My brain is not functioning anymore. I'm sure you've been there. I'm gonna grab some food and we'll figure this out. But hope you enjoyed this video. Hope you enjoyed some problems. It was an hour long. All right. Bye-bye.